Hello and welcome back to the course of Fundamental of Electronics and Electrical Engineering. The topic that I am going to discuss in today's video lecture is series RL circuit. I am going to analyze the series RL circuit. In the previous video lectures of AC circuit, I have discussed about analysis of purely inductive circuit, purely resistive circuit and purely capacitive circuit. And you know what we have to find whenever we are analyzing the AC circuit. So let us start with the analysis of series RL circuit. So here you can see a circuit consists of series combination of resistor and inductor. So here pure resistor and pure inductors are connected in series, and across this series combination one AC source, alternating voltage source V, is connected. As the source is alternating current will start to flow, which is represented by small I, that is nothing but the RMS value of the current. Now as the supply voltage is alternating, as the supply voltage is connected, which is represented by V is equal to Vm sin omega t. As the supply voltage is connected, current I will start to flow, and as current I will start to flow, there will be a potential difference across each component. That is, there will be a potential difference across resistor and potential difference across inductor. Now a potential difference across resistance is denoted by VR, and potential difference across inductor is denoted by VL. So we can write VL is nothing but the potential difference across inductor is nothing but the I into XL, and VR is the potential difference across the resistor, which is represented by VR, and VR is nothing but equal to I into R. Now as a circuit consists of only one loop, both elements are connected in series, the same current will flow in the series combination of this circuit, and that current is nothing but the RMS value of the instantaneous current. So current in this case is taken as a reference whenever we are drawing the phasor diagram. So whenever we are having a series combination of component, we will be taking current as a reference. So let us start with the first one, that is phasor diagram of series RL circuit. So as current I is taken as a reference, so I will be drawn in this direction. Alternating quantities are represented by phasor, so I is represented as a phasor. Now there are two components, resistor and inductor. Now we know for resistive circuit, voltage and current are in phase. So here in this case the voltage difference across resistor is denoted by VR. So VR and I will be in phase. So VR will be in same direction in the direction of I. Now in the case of pure inductor, we know current lags behind the applied voltage by 90 degree. As I is drawn in this direction, so VL will be in this direction. So voltage across inductor is represented by VL. So now you can see VL phase, VL is leading I by 90 degree, or we can say I lags VL by 90 degree. Now total voltage for the RL circuit is a phasor sum of voltage drop across R and voltage drop across L. That is, V is equal to phasor sum of VR and VL. So we have to find the resultant phasor, resultant component. So to find out the resultant voltage, we are taking the projection of VL over here. So now VL can be represented by I into XL. Now taking the projection of VL over here. So this is nothing but the VL. Now V is a resultant voltage, which is a phasor sum of VR and VL. So V will be in this direction. So this is nothing but the V, and V is represented by I into Z. How we are getting I into Z, that we are finding out. Now this phase angle between applied voltage and resultant current in this case is phi. It is not 90 degree because it is not purely inductive circuit. It consists of one resistor in series. So in this case, applied voltage and the phase angle between applied voltage and current is not 90 degree, but it is some angle that is represented by phi. Now from the phasor diagram we can write applied voltage is equal to phasor sum of VL and VR. So taking the finding out the magnitude of that, so we can write V is equal to square root of VR square plus VL square. So and we know VR is nothing but equal to IR and VL is equal to IXL. So putting that value over here, so V is equal to square root of IR whole square plus IXL whole square. Now taking I common from this square root, so V is equal to I in bracket R square plus XL square. So I is equal to V divided by square root of R square plus XL square, where we know V is equal to IR, where R is the some resistance, but in this case I is equal to V divided by something, so it will be opposition force, something opposition offered by the circuit, and that is nothing but the impedance. So in the case of AC circuit, impedance will come into the picture. So where square root of R square plus XL square is equal to impedance of the circuit, which is denoted by capital Z. So we can write I is equal to V divided by Z. This is similar to I is equal to V divided by R. In the case of DC circuit, we are having R. In the case of AC circuit, whenever there are more than one element connected, whenever there is series combination or parallel combination of the elements, so impedance will come into the picture, and impedance is represented by Z. So for this particular case, for the series RL circuit, impedance Z is equal to square root of R square plus XL square. Now phase angle. Now what is the phase angle that we are getting between applied voltage and resultant current? So suppose the angle is represented by phi. So from this triangle we can write tan phi is equal to VL divided by VR. Now putting the value of VL is equal to IXL and VR is equal to IR. So IXL divided by IR, I is cancelled from numerator and denominator, so finally tan phi is equal to XL divided by R. So phi is equal to tan inverse XL divided by R. This is nothing but the phase angle for series RL circuit. So from this phase angle, we can write down the expression, we can find out the expression of the current. So I is equal to expression of current, expression of voltage is V is equal to Vm sin omega t. Now current from this triangular we can see current is lagging behind the applied voltage by some angle phi, by not pi by 2, because this is not purely inductive circuit as I told you earlier. So as current is lagging behind the applied voltage, so angle will be negative, and the supply voltage is represented by V is equal to Vn sin omega t. So resulting current I will be equal to Im sin omega t minus angle, and angle is phi. So I is equal to Im sin omega t minus phi, but the value of phi will be in between 0 to pi by 2. So conclusion for RL circuit is that current lags behind applied voltage by an angle phi. Now the value of angle will be dependent on the value of XL and R. Now drawing the waveform of voltage and current simultaneously. So we know the expression of V is represented by Vm sin omega t, and I is the expression of I which we got is Im sin omega t minus phi. So in this case, suppose we are taking V as a reference signal because I is lagging behind the supply voltage, so V is taken over here. So V is starting from origin. So you can say one cycle is taken. The graph is V versus omega t. It is one cycle is taken between 0 to 2 pi. Now current I lags behind the voltage by some angle phi, and phi is in between 0 to pi by 2. So say this angle, this duration is phi. Now so current will be starting from this point. The duration of both voltage and current will remain same because frequency does not change. So this is the angle phi. So this is how you can draw the waveform of V and I for series RL circuit. Now finding the expression of instantaneous power and average power. So we know instantaneous power is a product of instantaneous value of voltage and instantaneous value of the current. So putting the value of V and I, so P is equal to Vm sin omega t into Im sin omega t minus phi. Now multiplying and dividing this expression by 2. So this expression become P is equal to Vm Im divided by 2 into 2 sin omega t into sin omega t minus phi. Now we know 2 as S. So P is equal to Vm Im divided by 2 into cos phi. If we solve this, we are getting cos phi minus cos 2 omega t minus phi. 2 SS is nothing but the C minus C. That is a trick to remember. So P is equal to Vm divided by 2 in bracket cos phi minus cos 2 omega t minus phi bracket complete. Now, so we are getting two terms from this expression of instantaneous power. So P is equal to Vm Im divided by 2 cos phi minus Vm Im divided by 2 cos 2 omega t minus phi. Now the first term is a constant term. Why? Because there is no time variable present in the first term. You can see here. There is no frequency variable present. In the second term, second omega t is present, second term. So it is a variable term, variable part, and this is a constant part of the instantaneous power. Now, finding out the average power from the expression of instantaneous power. So again writing down the same equation, P is equal to Im divided by cos phi, that is a constant term because it does not consist omega t terms, minus Vm Im divided by 2 cos 2 omega t minus phi, that is a variable term. Now Vm Im divided by 2 cos phi is a term which remains constant with respect to time, as I told you, that does not consist of any omega t terms, and second term is a variable term. Now in second term we are having 2 omega t term present. That means the frequency of this is double than the frequency of the supply frequency. So Vm Im divided by 2 cos 2 omega 2 t minus phi, which is a variable component as I told you, and which varies at a twice supply frequency. Now we know if we are taking the average of cos omega t, that will be 0. Now if we are taking the average of cos 2 omega t, that means we are doubling the frequency, but the number of positive cycle will be equal to number of negative cycle. So again average will be 0, and phi has nothing to do with the average because phi defines what? Phi represents the phase shift. The signal is shifted. So average of this term cos 2 omega t minus 5 is 0. If we take the integration from 0 to 2 pi, we are getting the 0. So by putting the value of the omega t, we find the average value of the variable part over a complete cycle is 0. Now the first term, average, the first term is a constant term, and we know average of any constant value is that value itself. So final average power becomes Vm Im divided by 2 cos phi, and this term is 0 as we discussed. Now this term can be written as Vm by root 2 into Im by root 2 cos phi. Putting by here we have taken 2 as a root 2 into root 2. Now we know Vm by root 2 is nothing but the Vrms, and Im by root 2 is nothing but the Irms. So final expression that we are getting is Vrms into Irms cos phi. That is the actual power consumed in the series RL circuit. In the case of inductive circuit, we found that average power is 0 because for the case of purely inductive circuit, in one cycle energy is stored and in other cycle energy is returned back. So for purely inductive circuit, we got the average power 0, but in the case of series combination of RL circuit, average power is not 0 because there is a phase angle phi present between supply voltage and resulting current, which is not pi by 2, but it is in between 0 to pi by 2. So this is the actual power consumed in series RL circuit. Now drawing the waveform of power using expression of using the waveform of voltage and current. So first drawing the waveform of voltage and current, V is equal to Vm sin omega t. This is a waveform of voltage, and this is a waveform of current which is lagging behind the voltage by some angle phi. Now drawing the waveform of power from the waveform of voltage and current. So here we are taking the small instances. So these are the small instants. Now here for this duration voltage is positive, and if we extend the waveform of the current, so current will be negative, so product will be also negative, and that will be instantaneous because both are instantaneous, voltage and current. Now from this, in this duration both are positive, so product will be positive, so we are getting the power, positive power in this duration. Now again this duration between these 2 points, voltage is negative and current is positive, so product will be negative, and in this duration both are negative, so product will be positive. So this is how you can draw the waveform of the power from the waveform of the voltage and current. Now here you can see average of this cycle is not 0, but we are getting average VI cos phi. Now moving towards the final thing, that is a power factor. So again taking the phasor diagram, voltage triangular. So we know power factor is the cosine of angle between voltage and current, the angle between voltage and current. So from this triangular, voltage triangular, we can write cos phi is equal to VR divided by V. Now VR is IR and V is a result. So phasor sum of VR and VL, and V is nothing but equal to IZ. So cos phi is R divided by Z, and that is nothing but the lagging. In bracket we have to write the lagging. Why? Because it is an inductive circuit. So this is the power factor of inductive circuit, that is cos phi is equal to R divided by Z, where Z is square root of R square plus XL square. So this is all about the today's video lecture. In this video lecture, I have discussed the analysis of series RL circuit. I have derived the expression of voltage, current, and we draw the waveform of voltage, current and power, and finally derive the expression of power factor. Hope you have enjoyed the video. Thank you for watching.